So today we're finished chapter 7, starting from 7.5. I should say this every time, Marinho, okay? Like which interval of chapters, because this helps me later to identify which video to post on YouTube.
Okay.
Cool. So we're gonna talk about impe- one moment. Pause. We're gonna talk about impedance, whatever. I already forgot the name, which is mixing different computational models in a single program. We're gonna talk about more parallels between OOP and high order programming, and beyond, because there's a lot of stuff. Okay, so the first thing that matters, I think, is the parallel between OOP and high order programming. So there is a very cool example. Yeah, actually, this is the cool example. You can make the same kind of thing using classes as you would do with a high order function. So in this first
Wow.
example, we have a procedure that takes called new sort routine that takes order and outputs something, well, which is another procedure. And we have this sort routine class that you initialize with the comparison, the ordering thing. And then these two things kind of do the same thing. So the book emphasizes this parallel between high order programming and OOP.
Yeah, they're semantically equivalent, basically. There may be some details about mutability, but in general, they are the same thing.
Yeah, embellishments added by object-oriented programming. So there's a lot of thingies such as explicit state. Our OOP uses explicit state procedures not necessarily. We have multiple methods that share the same explicit state due to lexicoscoping. We can create classes, which is just syntax sugar. We have inheritance and degrees of encapsulation. So those are the more convenient things that you can do using OOP. Um, and then here are some common limitations in more popular OOP systems, such as classes as values. They can be created at runtime, pass as arguments, and stored in data structures. That's not everybody can do that. Full lexicoscoping, again. Actually, I don't know any language aside from Oz that can do that. Do you know, Marie?
Well, any scheme dialect, common Lisp, for instance.
I never exploited that in Common Lisp before. But well, I was not
Well,
actually used to thinking of lexicoscoping, of using lexicoscoping this way. So it was sort of a skill issue on my part.
I guess also pretty much any functional language, because they're also based on the lambda calculus, which does have full lexical scoping when it's fully implemented, right?
Yeah, but you cannot, like, like aside from I'm not getting it. I don't think Haskell does that.
Well, Haskell is pure, but you can do this in OCaml, for instance.
Wait, you can do the Inokemo the same thing about. Okay, I have a value that this function. Well, I have a scope that I have a value, and I have a function that I will export out of this scope that uses this value.
You can do
And
this in Haskell as well. It's just that Haskell doesn't have mutable state that you can put in there, right?
oh, okay, full in Inokemo we would use references, a reference to do that.
Yeah.
Okay, then that's fine. Then I completely understand. It's because in OS, logic variables is also part of a thing. Cool. And then you have first class messages, which is well, I don't know any language aside from Smalltalk that actually takes this concept of message passing in OOP seriously. In OS, I should say as well. Uh,
Uh, I mean, if you interpret OCaml processes as objects, then messages are first class there, obviously, but not many people do that.
I never used OCaml processes.
Oh, not OCaml, I meant Erlang. I don't know why
Oh,
I had
okay.
OCaml in
Erlang,
mind.
I completely agree. Okay, so mixing the batcher adds the ability to any other class. Some OOP languages not full support do not support full high order programming because they cannot define procedures values with access scoping at runtime. In
Actually, with modern C++, you do have that. but you have to be explicit about what are you capturing from the environment because you have to allocate memory for that, right?
Yeah, that makes sense. In these languages, many of the abilities of hardware programming can be obtained through encapsulation of inheritance. Well, you can kind of do this the trick of full access scoping by using a class, right? So you have an attribute that all the methods have access to.
Yeah, you can use the whole relationship between classes and higher order functions to kind of fake this in languages that have classes but not higher order functions.
Yeah, and the generic class, which is like the sorting thing, you can use an abstract class to do that. Um, yeah, the object attributes represent the procedures, values, external references, and and they are external because the attributes are supposed to go with the constructor, with the init, so they come from
Yep.
above. When the object is created, its attributes are initialized with external references. Then the object can be passed around, just like a normal procedure, with a little bit of discipline from the programmer. This allows for programming with procedure values. And then the abstract class. The generic procedure is one that takes procedure arguments and returns a specific procedure. For example, a generic sorting routine can take a comparison operation for a given type and return a sorting routine that sorts arrays of that type. So you would use an abstract class for this. Um, an abstract class is a class with undefined methods. Yeah, and then concrete classes, which you're going to see later, are the one that implement those things.
Yep.
Encoding procedure values as objects. So this is very silly, but in theory, you can make a function, like a procedure, a class, and you have an apply method that actually does the application. In this particular case, with just two things, x and y.
You know what the sad part is, Lemos?
What?
Closure needs to be implemented like this under the hood because it runs on the JVM.
That's very silly. Well, but I guess it makes total sense, right? Because what else would you do if you have to be on the JVM?
Yeah, yeah,
So like, I can't blame them. I can blame them for the choice of VM, but if they already have chosen the VM, this is silly, but you have to go do this anyway. I guess this is how they may probably this is how closures are implemented then.
yeah. Basically, there's an iPhone interface defined in the closure.lang namespace, if I'm not mistaken, which has a bunch of apply methods for the different arities, and you just have to implement that
Wow,
for.
arity by arity, huh?
Yeah, they do that for efficiency because if you just did a single variadic signature, you have to do packing and unpacking of the arguments every time, right?
They could generate that at the compile time if they had in a very different dystopian future if they had compile time reflection. Like they could
They
generate that.
could, but it's Java.
Yeah. Function decomposition versus type decomposition. This is very interesting. So here is this is actually a parallel that I never thought before. So this is basically doing a contrast between having a type and having a bunch of operations and how would you implement them in a pure functional based way and how we would do that with an ADT. And the thing of the matter is that the trade-offs are reversed. So if you have a bunch of functions and you have to pattern match on all the possible cases of it, if you extend the type, you have to change all of the functions because all of them will probably be doing pattern matching. But on
Yeah,
the
this
type
is.
decomposition, you don't have to necessarily because they are kind of like separate. They are individual entities, each subclass of the thing. But the
Yeah,
other thing is also true. If you have to add a function to all of those types, then it's easier to do it in this one because you just add one a single function. But in this case, you have to go through all the classes and add the function.
yeah, that's called the expression problem, and it's kind of a big deal.
I never heard the expression problem stated in the way that I just did.
Uh, well, to be fair, the expression problem has an additional constraint that is, okay, I want to be able to have my data types and have operations on the data types, and I want to be able to extend both the data types and the operations without recompiling the code, right? That's the additional constraint. But fundamentally, the issue is okay. I have a way. I need to figure out a way to organize the code in such a way that it's easy to do both things, and that's not trivial actually.
Well, the first way that you stated, which is I want to extend the thing without having to recompile, you just need a very dynamic language, no? To do that.
Not
Only that. Just that.
well, not really, because you can do it in OCaml perfectly well.
But you're gonna have to recompile.
No, actually, if you use tagless final style, that actually solves the expression problem.
Ah, okay. The thing that you explained, the tagless final. Uh, well, but you still have to recompile the program. You're adding a new function for the tagless thing. When
No,
you said I don't have to, I
because
don't want to recompile, is like I already have compiled a .o program.
you don't have to lemos, because remember, functors are potentially compiled independently, right?
Yes,
And if you want to add a new operation in tagless final style, that's a new functor lemos.
that's a new
So
functor. That's not just changing an old one.
it's a new functor, which means you don't have to recompile the functors that already exist, you see?
Ah, okay. Now I see. Okay. Yeah. So this parallel expression problem, very cool. I never thought about it, although I already stumbled upon the expression problem. People mentioning to me. Yeah, and there is a good guideline here. When designing a program, it is good to ask oneself what kind of a modification is most important. If the type is relatively simple and there are a large number of operations, then the functional approach is usually clearer. If the type is complex with a relatively small number of operations, then the type approach can be clearer. Um, Usually, none of those cases are true. So if not
Yeah.
using tagless final, such as we are not in the Erlang thing, the types are complex and we have many operations on them. So
Yeah.
it's like the worst of both worlds. So there's that. Should everything be an object? So this is kind of the related to the function being an object. And then the book makes a distinction between strong objects. So, um, so if you have these five properties, you are in a strong object, all a strong object language. All language entities should be defined by classes, be extensible with inherents, have a unique identity, encapsulate a state, and be accessed with a uniform syntax. So this is pure. If your language fulfills these five properties, it's a pure strong object language. The desire for purity can lead to good things. For example, many languages have a concept of exception to handle abnormal events during execution. It can be quite convenient for exceptions to be objects within inherent hierarchy. This allows for extending them. So this is a very usual problem of like I have an error type, like an error tag union, but I don't know all the possible errors because I have to interact with a third party. So usually one of the possible solutions to this problem is to just have a catch-all error that holds usually a string, because then you're gonna just put whatever the error message is that you don't know what it is inside that, and then you just pattern match on that, which is usually not the great experience because you want to be able to classify those errors. And with inherents, you can have well, in a dynamic language, you can have all of these like better. Smalltalk 80 is a good example of a language for which purity of an explicit was an explicit design goal. In most languages, not all entities are strong objects. So then we have a bunch of examples. Java, an integer is a pure value, a primitive, not an object. An array in Java cannot be extended with inheritance. Arrays behave as if they were defined in a final class. Should a language have only strong objects? No. First, stateless entities can play an important role, such as declarative programming. Um,
OCaml mentioned.
Objective or camel mention?
Well, the O means objective, so yeah,
Yeah,
OCaml
but
mentioned.
nobody writes it like that. In addition, stateless entities are essential for making transparent distributed programming practical. I don't know that yet. Second, not all entities need a unique identity. For example, structured entities such as tuples in a database are identified by their contents, not by their names. Yeah, this is kind of like a hot take, no? Yeah.
Well, but it's true.
Well, but I understand, but not everybody would agree with that.
Well, those people would be wrong.
Third, the simplicity of a uniform syntax is illusory. We seem to be removing each property one by one. We are left with two principles. All language entities should be instances of ADTs, and uniformity among ADTs should be exploited when it is reasonable. For ADTs, some ADTs will have all the properties of strong objects, others will have only some of these properties, but also have some other completely different. The yeah. So objects in an explicit state. Uh, Given a particular object, how can one predict its future behavior? Its internal state, which is like time related, its textual definition, which is space related. We see that the semantics of an object is spread out over both time and space. This makes an object hard to understand in a function. The semantics of a function is all concentrated in one place. Yeah, this is kind of a hot take as well, because if you have a pile of 50 nested function calls, then it's not really concentrated in a single place. But what I think they meant by saying this is that you can treat the final box as a black box, and if it's a pure function, you just need to care about what comes in and what comes out. You don't have to care about other miscellaneous mutable things going on all over the place.
Yeah, immutability is generally good for locality, usually.
Yeah, the function does not have a history. It depends only on its definition and its arguments. If it's a pure function. Uh, yeah, so if we're doing floating point arithmetic, uh, yeah, this is very tragic because this is changing potentially via a global variable the rounding strategy in the middle of the program. And then the following operations, assuming that the roundness was done in a particular way, they will be completely fucked.
Yeah,
Um, yeah, to avoid this problem as much as possible, the language should not favor explicit stated inheritance. That is, not using them should be easy. For inheritance, this is almost never a problem, since it is always harder to use it than to avoid it. For explicit state, it depends on the language. In OOP model of this chapter, defining stateless functions is actually slightly easier than defining stateful objects. Objects need to be defined as instances of a classes, which themselves are defined with a class syntax, wrapping one or more math declarations. Yeah, in popular OOP languages, unfortunately and sadly, explicit state is almost always the default, and functions are usually syntactically cumbersome. I think this is like I'm gonna make the pun. This is inherited from the C world, no?
the part about explicit states being the default, yes, but functions, not really actually.
No, but that part is like nobody cares about that part. Everybody cares about this. So I
Yeah, no,
think
that is definitely inherited from C in the modern OOP languages.
yeah, so everybody was doing mutation anyway, and they just wanted to have methods and things and to have a way to extract the commonalities. So they actually kept the mutability model, but just added the classes and the inheritance things.
The problem is that most, like pretty much every OOP language evolved from ultimately assembly, right? So
No,
in assembly, mutable is the default. So that's just kind of the path of least
but that
resistance, I
but
guess.
that's man, every like Haskell compiles to assembly. Like what are we talking?
But well, Haskell compiles to assembly, but it didn't evolve from assembly. It evolved from the lambda calculus.
Um, the problem with the cons, like I understand what you're saying, is the problem that evolution kind of like has a tree, and we cannot deny that the most common ancestor of every compiled programming language is assembly. Like
Not
when you
compiled,
when you
only
say
being.
evolve, you are talking like metaphorically, right? You're talking more
I'm
like
talking
the
about no, no.
spirit.
I'm talking about the chain of concepts and where they came from. So, for instance,
Yeah, so
Lisp,
metaphorically.
well, yes, Lisp was created originally. Well, it was intended to be compiled down to a particular for a particular hardware, but it borrowed the syntax of the lambda calculus for whatever reason, right?
Yeah. Uh, yeah, sure. But metaphorically makes complete sense. So it's the key concept, the key idea that we are drinking from. So yes, it is a different sort of evolution. Um, Uniform object syntax. Yeah, this is for Nathan. Nathan is not here, and he probably never gonna watch this, but he will be pretty inflamed by this because Nathan believes that syntax doesn't really matter, and what matters is the semantics. Are the
Oh,
semantics?
like even in Lisp, where you have almost no syntax, the little syntax that you do have still matters. So,
Yeah, but how should I say this? Nathan thinks that syntax matters in the sense of familiarity. So if I give you an APL, the syntax is bad not because there's an objective criteria, according to Nathan. It's because you're not used to it. You didn't know. You're not educated on how to read it. Which he's partially correct. Like when you start getting to Lisps and S expressions, after some time re-educating yourself, it's okay. But Mageta, and I think I am on the side of Mageta. Mageta is more like, no, 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 no. There is a separate, a separate, how should I say this?
like even if it takes the syntax in isolation, it can be suggestive of
Yes,
certain ideas, right?
yes, exactly. And then the usual example that Mageta brings is the let in from OCaml that was removed in F sharp. That in OCaml, by having the syntax preserving the in the let thing, it still reminds you that this is just a lambda. But the let without the in F sharp was, one moment.
It looks like assignment, right? Vaguely. That's kind of the issue that I heard Mageta talking about.
Exactly, exactly. But I'll be back. Sorry about that.
No problem.
Yeah, so the syntax, so it's exactly what you said. So the syntax can still convey on its own, like standing on its own, can still convey some ideas. And this is essentially what the paragraph is describing. That in COBOL, for some random reason, they have a particular piece of syntax that describes the opposite of the order of what's being checked, and that's not good. Should all
Yeah.
operations on language entities have the same syntax? This does not necessarily improve readability. For example, Scheme has a uniform syntax which does not necessarily make it more readable. We find that a uniform syntax just moves the richness of the language away from the syntax and into the names of objects and classes. This adds a second layer of syntax, making the language more verbose. Let us give an example. So, apparently this is called symbolic programming, which, uh, sure.
Yeah, that's a very old term from the AI folks, actually.
And then, yeah, this is the problem. This is the we've seen this before, right? We've seen in the last
We
session
did. Yeah,
this
we
thing,
did.
and it looked terrible back then, and it still looks terrible now.
Well, it is pretty terrible on its own, regardless of when you look at it.
And the reason is because, um, well, I don't think this argument is very sound because it's kind of saying that, hey, uniform syntax is bad. Here's an example, but I don't think this crucifies the idea. This crucifies this particular implementation. Uh,
Yeah,
so I
yeah.
don't know. I like the idea of having uniform syntax. Jonathan talks about that in his new programming language talks from 10 years ago.
I actually like the way Clojure approaches this with the EDN syntax, which is basically an extension of S expressions, right?
Yes.
It just says, okay, S
Yes.
expressions are basically a good idea, but let's add syntax for more built-in data types, right? Like vectors and dictionaries and
And
so
yeah,
on.
maps and sets, and that's good. And this is C++ syntax, which is similar to Java syntax. For decomposing a list value, there is another natural notation using pattern matching.
Hello,
Uh,
Nathan.
hello. Pattern matching is commonly used in symbolic languages. This is also cumbersome to do in uniform object syntax. Yeah, this is the problem. You want to make it uniform, but you want to make it object based. There is a
You
further
know what the
in
silly,
go on.
you know what the silly part is actually? Java 20 something, I don't remember the exact version. They actually added pattern matching, like flat out.
Finally. uh, this is because the uniform syntax requires explicit synchronization. This is not true for the case syntax above. Well, which is sufficient for concurrent programming if the computation model does not implicit the does implicit data flow synchronization. Yeah, so this is there's a big if in there. So if you're doing a receive in Erlang or doing a case in OS, then sure, we are good. But if your case doesn't have this, then it may be a pain in the fucking ass. Um yeah, another more realistic example is a graphical user interface inspired by this tool. Christoph built a Java prototype of a similar tool. The Java version is more cumbersome to use than the OZ version, primarily because Java has no syntactic support for record values, which is very
it,
unfortunate.
it does now, as of 2017, 2018, I think.
Unfortunately, this verbosity is inherent property of Java. There's no simple way around it. Well, apparently there is a simple way around it. Well, maybe not simple.
Yeah, you just have to update your Java from version 6 to version 20, whatever.
Yeah. Implementing the object system. So now we're not gonna go all the way to the kernel language things and re-implement the things and stuff, but you're gonna see a more throughout explanation how to implement the object system. What part of this matters? The distinction between abstract and concrete class matters. So an abstract class is a class in which some methods are called but have no definition in the class. A concrete class is a class in which all methods that are called are also defined. Yeah, but here's the cool trick. If you have a method that I think it's written in here. If first class matches are supported by the language, then invocations of the form are possible where m is calculated at runtime. If such an invocation exists in the program, then the distinction between abstract and concrete classes disappears. And the reason is because it, the methods are just message passing, which means that you can use the otherwise anyway. So, like, it doesn't need to be defined. You can just use the otherwise.
That's an option, yeah.
Executing the invocation raises an exception if m does not exist in object. Well, not necessarily, right? Because you can use the otherwise. Am I writing this?
Well,
Am I reading this wrong?
yeah, no, you are correct.
Yeah. Yeah, this is a cool thing. This is a cool diagram. So you have a running object. So uh, well, it's an object plus a thread. So this is not a running object. This is an active object.
Not quite, because it can be an object that you just sent a message to and it's running the method, right? Doesn't necessarily have to be an active object. Could
But
be
it's written
passive, but you
thread. You
just
don't have a
called it.
thread in what you said.
You do, actually.
Where?
Well, the thread that you did the calling is going to execute the code of the method.
Yeah, but that's synchronous. That's in the same thread as the instantiation of the object.
Well, it's in the same thread, but it's still a thread, Lemus. That's the point.
But then this doesn't add anything.
It does,
Oh,
because there's...
wait. It does because the keyword is running. So this is mentioning the thread because it wants you to understand that this is doing something.
Yeah,
Okay. Not great. Just keep running here. Especially because active objects is right below this. But okay, and then you have the object, which is just a procedure that encapsulates an explicit state and a set of procedures that reference the state. Then you have the concrete class, which inherits from the abstract class, which makes sense. And all of those are instances of a meta class. And I think the meta class is the most interesting. A meta class is a class with a particular set of methods that correspond to the basic operations of a class. For example, object creation, inheritance policy, method call, method return, choice of a method to call, attribute assignment, attribute access, self-call. Writing these methods allow to customize the semantics of objects. So this is the meta. This is the class that does the meta object protocol. 24 is the thing. Yeah, nothing too crazy about this. And then implementing classes. So now we have this piece of code that is transcribed to this piece of code. And then my question, which I think may be a dumb question, why the heck do we need self in here?
Because in general, you don't know the self until the method is actually called.
In general, you don't know the self,
Well, you can't know the self until the method is actually called.
but I'm not using it for anything.
Well, not in this particular method, but in other methods you could.
Hmm. Well, I guess that's true, but like bad example then. But well, I guess they just wanted to keep reusing the counter another one once more. Implementing objects. So this is just explaining. Yeah. Then we have the new definition, which I think we've seen before. This is exploiting the state using lexicoscope for the object procedure. So this is the state. So this is the security thing. So this is doing an unwrap because if you read this, we're doing a wrap on it.
Yeah.
Then we create a state, the initial state of the object. We initialize all the cells of the attributes. Uh, yes. Then we're creating an object procedure that we're going to provide at the end that are methods label m. Where is label coming from?
Label is a built-in that we saw way back at the beginning. It takes a tuple and extracts the atomic label of the tuple.
Yeah, but what is this doing? You know,
Well, it's taking the label of the
this is a self.
message to look up the
Oh, this is
method.
oh, this is the method. Okay, never mind then. This is just calling a thing. This is just calling something. And then you initialize it by calling the init method, and you return such procedure. So it's fine. Then we go to implementing inheritance, which uses where is the code? This code. Um, and this code does a lot of stuff because it has to check for conflicts between the classes, the
It
C2 and the
does.
C3. And I actually didn't know this, but if you have a conflict, but the base one also has, the conflict is solved by the first one.
Yeah, because like if you have an ancestor's methods that you have two ancestors that have the same method so they conflict with each other, but you are overriding that method anyways, then the conflict actually doesn't matter.
Ah, I got confused because this is wrong. This should be C1, not
Well, the
C.
C1 would be the anonymous thing that is the body of this thing, right?
Yeah, but then that doesn't make sense to me. The C1 should be this C1, and then this is the body of C1. That's fine, but
No, no, no. The class C is the output of the from.
exactly, you're defining C1 that is inheriting from C2 and C3. That's what this code does, no?
No, 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 no. You are defining C, which inherits from C2 and C3, and C1, which is actually the body of the C.
But why are we making this distinction? This is the body of C. Why are you giving C1 name?
Because C1 doesn't have all the fields that C2 and C3 have, but C does because it inherits from all three of them.
No, that's what you said doesn't imply different names still. I'm having a hard time understanding, okay, why don't you put C1 here or put C here?
You can't put C inside of that because that's a circular dependency.
No. the way that it's written base class. I understand. Why just not call body of C in here? What are you
I mean, you
losing?
could. I mean, you could, I guess.
Yeah, this is just confused me. I was asking, okay, where is C1 coming from in this shit? It's written in here, the base class C1, but this is wrong because to have a base class, you need to put in the from. So where is C1 in here to be the base? I was like, what
Um,
are you guys talking about?
it's being inserted by the compilation process. It doesn't actually exist in your mind because you think of it as C, but for the details of the compilation, yeah, this actually matters.
Okay,
And
that
this is a result of the particular strategy, the particular compilation strategy that they chose. They could have done something different, but they didn't.
yeah, the strategy could be kept the same. I just think that these names are bad. That's my opinion.
That's
Uh,
also fair.
I don't see what are you losing by just saying body of C here. I don't see. But okay. Um, so blah blah blah. Java is a pure object-oriented language, but they have primitives such as integers, floats, and booleans and characters. It has simple semantics apparently.
It
Uh,
does. The only problem is that it's ridiculously verbose. Or it was. It's less verbose nowadays if you're allowed to use like Java 20 or whatever.
yeah. Computation model. So Java consists of statically typed or OOP with classes, passive objects, and threads. The Java computation model is close to the shared state concurrent model, minus the flow variables, of course, because nobody has those. Triggers and names. I don't even remember triggers anymore, to be honest.
A trigger is a procedure that's attached to a data flow variable that is only run when you block on the variable.
Ah, okay, I remember.
And it's used to implement laziness, basically.
Parameter passing is done by value, both for primitive types and object references. Newly created variables are given a default initial value. It depends on their type. There is support for single assignment. Variables and object attributes can be declared as final, which means that the variable can be assigned exactly once. Final variables must be assigned before they are used. Uh, and they have different nomenclature. But that doesn't really
They
matter.
do.
They try to solve the multi-inheritance thing by using interfaces, which, well, sort of, because the only way that this will work is that every attribute of all the multi-inheritance thing, they have getters, so you can access them, and the interface makes you use them. Because if I have an attribute on a different class, and I have an like X on A and Y on B, and I want to have both in a C, I cannot do just multi-inheritance in Java, so I need to use the interface. And the interface needs to somehow manage this problem of allowing me to have both X and Y. So I don't find that particularly cool.
Well, interfaces don't allow you to define fields. They only allow you to define methods.
Exactly. That's why I mentioned that you have to have a getter
Yeah.
somehow. Uh, so Java supports multi-inheritance for interfaces. And I think this caveat that we just mentioned, they should have mentioned in here. So apparently you can have an inner class in Java, which I never used, which is a class definition that is nested inside another class. An instance of an inner class can be passed outside of the method body or code block. An inner class can have
Yeah,
external references. Go on.
in old versions of Java, before they added the lambda syntax sugar, um, if you wanted to if you wanted to return a procedure, you had to do something called an anonymous inner class, which is kind of cursed.
Okay. Um, but this also reminded me of Zig. This thing. Because you need to pass a
Yes.
struct. Like,
Well, yes, but Zig has a different reasoning for
no,
this.
no, no.
Like,
There's a completely different reasoning. I understand. It's because of the closure problem. That's fine. But just this sentence, an instance of an inner class can be passed outside of the method. Like you can literally define a struct inside the body of the function. Like external that.
Yeah.
Uh, in a class can have external references, but there is a restriction if it is nested in the code block. We could say that an instance of an inner class is almost a procedure value. The restriction likely exists because of the language designers want the non-final variables in code blocks to be implementable on a stack, which should be popped when exiting the method. Without the restriction, this might create dangling references. So this is also a closure problem.
It is actually.
Damn, everybody's suffering from closure problems. Um, okay, and then there is this very random section, which is teaching with Java and the parallels between it and OS. I don't think there's anything interesting to mention about this, do you?
Uh, Not really.
Yeah, and then you need to be very careful about the streams in Java are not the streams in OS. They have the same name, but they mean completely different things. And then there's an example of a point. This is how you would do it in OS. Then you would extend the point. Well, not extended with inheritance, but you'd add an add to it, and the add would do this. Um, and I like that this actually makes the message passing very explicit. And in here is just like a dot.
Yeah.
Parameter passing in main program. So there is a like call by value and call by reference for objects, and everything else is called by value apparently. So this is another example of a program. You have the main, you have your integer, and you have a call example that does all of those things. And then you have inheritance that pixel extends the point. We assume there's a color, and we can extend stuff to it. And then finally, oh, and this is how you would do that in OS. And then
Yep.
finally, we have active objects. So active objects, it's essentially an object with a thread inside. So you have this new active abstraction that gives you an object, creates P, which is going to be our port, and then you just spawn, which means that this is asynchronous now. You spawn a thread that will do an interaction between the port and the object. And then you return this procedure here that receives the message and just sends it to to block it in here.
Yep.
And then the thread keeps doing the thing that we read before. So apparently, if you're not doing this, the objects are called passive, which I think would be funnier to call them deactive, not passive. But
Why?
I don't know. I just think it's cooler. It's like deactive. Because passive usually has a very negative connotation in like English. Anyway, so then we go to this problem, which we're gonna solve using active objects, which is very tragic. So there's a circle of people, and we're gonna count starting from one. We're gonna count to three, and the lucky person on the third position will be dying. And then we just continue. So 1, 2, 3 dead. So all multiples of 3 will die, but then the counting after we're done with the first circle, we recount everybody and then we start the process again. And the
Yeah,
question
it
is
wraps around.
who's gonna be the last survivor? And we're gonna implement this problem. But this is the code to do that in OS, of course. But what's more important, where is it? Yeah, this is the object version of this problem. So we are defining a class for it.
Yep.
And there is an optimization. There's an optimization that we are removing the dead bodies. And there is a footnote in the new version. I wonder if they already had it. Okay,
Yeah.
they changed it. Okay, so the footnote on the new version is a student made a reminder that a dead person is a kind of a zombie or something like that, or a or maybe they kept the dead object. But there was a prefix now saying that a student raised their hand or something and mentioned that.
Okay, I like the attribution in the new version, but this is
Uh,
funny regardless.
yeah, this is very funny. And then we made the same program using a declarative version. The declarative version is smaller, but in my opinion, it's harder to read. I can explain why. The reason this is harder is because where is less coming from? Like this is just being used everywhere, but I don't know where it is.
Well, it's declared there
Oh,
as
here.
a free variable. Yeah.
Yeah, this is just free. I thought this was like a function application or something.
No, it's initially free. It gets bound when everything finishes.
Yeah. Yeah, but this is essentially these two pieces of code are essentially doing the same thing. The rules are pretty straightforward. Like nothing here is that like, oh my god. The only thing that you need to pay attention is that we're doing the short circuit optimization, which is to just remove the dead bodies. And then we compare that with the declarative solution. We notice that it's smaller. It does a short circuiting. It's half the size. One reason that streams are first class entities is to make short circuiting very easy. Just return the input stream as output. And then this is the declarative version. Other active object abstraction. So now we're going to try to re-implement some of the object abstractions we see before, such as RMI, which is to make it synchronous. Because when you make it the active object, you made it asynchronous. So to make it synchronous, it's just easy. You just do an await on it. And you need to have a variable like to be waiting on. So you're gonna have an x. So this and using the same tuple trick that we already used this trick before. I don't remember
Yeah.
where, but we did.
Oh, one thing actually we should note. This was mentioned like way back when we were looking at chapter 5 that the book made an aside that, oh, in Erlang you program with active objects, which are basically a port and a thread, right?
Oh, but in
But now we
Erlang you
finally
also have
know,
the mailbox, right?
yeah, with the mailbox. But now we finally have a definition for an active object, the asynchronous version. And if you look at that, you'll be like, yeah, actually this is basically an Erlang process.
Yeah. Well, it doesn't have the receive semantics, but yes, it's
Well,
close.
but it does. Each method is basically a case in your receive.
No, 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 no. But the receive semantics imply that the order doesn't matter, right?
Oh, right. You can pattern match on things out of order with
Yeah.
receive. That is
This
true.
for doesn't do that. I remember, man. I remember. I told you. I will remember this. Uh, yeah. So pretty cool. So that's the RMI, and then we have the exception handling. So this is again, we used this trick before, 100%, which is to give you a way to give me an indication of an exception when from the caller perspective. So I called you, I passed the ball to you, something exploded, and instead of just exploding, you just give me I will give you an inbound variable. You tell me the outcome, and I will inspect that myself later. And this is what it's happening here. Of course, this also means that you can explode if you want. So um, for the synchronous case, you can put the case statement inside the abstraction. So this, um, well, actually, this is the caller. So this is why this guy is exploding. It's because we are just inspecting the E.
Yep.
Uh, yeah, but where is E coming from? I just noticed that. What is this? Wait a moment.
Oh, it's from the.
There is a trick
Actually,
here.
no, it isn't.
Where is E coming from?
That should be X, I think.
Yeah, this should be X, right?
Yeah, it should.
Okay, so there is a typo in the book. Event manager with the active object. So this is a very simple event plan manager application that we're going to use multiple computation models to solve the problem. So we start by making a class of the event manager, which has um, well, actually we need to read this to make sense. So each handler is a triple ID, F, and S, where ID uniquely identifies the handler, F is the state update function, and S is the handler state. Cool. When an event E occurs, each triple is replaced by this. That is, each event handler is a finite state machine which does a transition from S to state that when the event E occurs. Yeah, so
Oh,
E.
this is mentioned again here about the Erlang thing.
Yeah, the event manager was originally written in Erlang. The Erlang computation model is based on communicating active objects. Yeah, you can implement the same problem using Erlang message passing. And then the event thing posts an event to the event manager. The add adds a handler, and the delete deletes a handler. And the reason we need ID is just to identify them. Then we create a new active object with the event manager, which means that it's asynchronous by nature. And then we can just plug stuff into it. So we have the state transition function, and we can just add stuff to it. So this is going to be the state transition function. This is the initial state, and this is the ID. Yeah, so we're using the trick with the dollar thing. We can replace the memory-based handler by a disk handler during execution without losing any of the already logged events. Again, dynamic language. Well, but I guess you could do this with high order functions as well in a static language. Just less convenient, but you can. And then you can make the disk handler thing, and then you can open a file. You can delete the previous handler that we had before. Wait, but deleting the handler.
It
Yeah,
just removes the
that's.
handler from the list, basically.
Yeah, but we don't want to lose the logs, right? So where are we saving the logs? Not here.
Uh, no,
We're
it's
not
not there. It's down
saving.
there in the. Where is it?
Yeah, this is the buffer.
The,
This is the buffer of logs, right?
yeah, that's the buffer.
Yeah, so what are we doing here?
It's in replace.
The delete returns the buffer of logs? Oh, it does.
Oh, it returns the final state. Okay.
Returns the final state. Oh, DS, you mean.
Yeah.
What is this? What is this syntax? Is this a triple with like nothing in the first and the second?
List dot partition. It passes the previous handlers and then this function and then this list. Okay.
Yeah, whatever it does apparently returns the buffer of logs. So that's what we are doing. And we are reusing the, well, actually, which is kind of funny, we are reversing it. And the reason we are oh, it's because they are,
They're using linked lists without using the difference list trick. So the log is actually
oh
backwards.
yeah, so it's backwards because of the const. So they are reversing it to write to the, yeah, this is annoying. You have to grab your new, we would use a functor for this, right, in OCaml? Definitely.
Yeah.
Like this class would be a functor, this thing. And then the implementations, well, but that's the thing. I think we would all still have to do this in the OCaml version. We have to grab the previous one and rewrite it in the new one. But it
Yeah.
would be kind of nice to like provide a transition function. Like I have the old one, I have a new one. I give you a lambda that teaches how to transition them, like migrations.
Yeah.
And then you add a new handler for the disk. And then adding functionality with inheritance. So now we want to add batching to it. So we now have the replace event handler, which is this one. So this inherits from the event manager, but it has a replace thing that essentially. Oh, why are we doing this? Because between this between all of these three lines, we can stop the execution and do something else. So that means that we have a potential
We can
um,
potentially lose events while we are translating to the new buffer, the
lose
disk buffer.
events. Oh, lose events because we are wasting time doing the transition, doing the migration.
Yeah, because you remove the old buffer
Yeah, as soon
and
as
then you
this is
start writing
done,
to the
we
disk.
may receive events, right?
Yeah, but we may receive another event in between, and that's not going to be logged.
Yeah, and then the replace event manager is the one that does both of the operations. So it grabs the buffer and then it applies the new one, but it returns a new one uh,
Yeah,
with
because
the
of the
thing
semantics
swapped.
of Yeah, because of the semantics of the active objects, since you're using a port, every method call is basically transactional. This is only a
Yeah,
single method, so it's atomic from the point of view of the.
yeah, and that's the cool part because we gain this for free by making this class. We already have atomicity, right? Atomic,
Well, if
transactional,
you're using active objects, yes.
and then we can do the same with well, we're gonna see a batcher extension as well. But then this is how we would use the replace, which is very cool. And then we have the batching, which essentially extends the thing to have a batcher. So you have a batching event manager that uses the inherits from event manager and batcher, and then what it does is inherits from this. So it has a batch function, a batch method, I should say, and then you can just use the batch here using a delete. So you can do a bunch of things, like a bunch of transactions, right?
Yep.
Yeah, but you can receive messages between them, can you?
No, because batch is itself a message.
Yes, matches itself a message. So all of these are in combining. So this is essentially a way to compose transactions.
Yes.
Cool. Combining computational models. So now we go back to the impedance thing that I said in the beginning, almost 1 hour ago, that we are combining. So the event handler is defined declarative by its state update function. We have all methods that execute in sequential fashion as if they were in a stateful model with no concurrency. All concurrency is managed by the active object abstraction as implemented by the new active. New functionality, for example, is done by object inheritance. And the result is that event handlers are defined sequentially and declaratively, and yet can be used in a stateful concurrent environment. So this is what the impedance matching does. You can give some properties of having a sequential and declarative program, even though its implementation in the hood is a stateful concurrent environment. But like, come on, you need to be very skillful like not necessarily in this example, but probably in real world examples with all of this power, you need to be able to like have some skill to identify. Okay, I'm gonna use this from that and this from this and put in a all in a big thing and mix it up, and everything is gonna be okay.
Yeah, you have to have a good eye to identify how you're going to layer the models, right?
Now you can be wrong and you can make mistakes. Impedance matching is a special case of general principle of separation of concerns. The concerns of state and concurrency are separated from the definition of the event handlers. It is good programming practice to separate concerns as much as possible. Using different computational models together often helps to achieve separation of concerns. And that's it, with 3 minutes to go to 1 hour.
Yeah. Next session is after your vacation,
Yeah,
and we're
so we're
going to
only gonna
chapter
talk about
8.
this New Year's.
Yeah.
Well, after New Year's, it's already gonna be 2026. So next time we're gonna talk about chapter 8. So let's see how much.
This is one of the most complex chapters in the book, by the way,
Damn. Okay.
because shared state concurrency is hard because you have state which is shared, and you have multiple threads poking at that shared state simultaneously. So you have to deal with that.
Okay. So we have 23 pages going from 8 all the way to 8.3. Do you think that's too much?
Um, no, I think
23
that's okay
pages.
actually. I think that's okay.
Okay. So let me save that. So next session 8 to 8.3.
Yeah, in this chapter we're gonna talk about transactions. Nageta would be
Transactions.
proud.
Nageta would be proud. And then finally, the one that I'm most excited about. What is the fucking difference between relational and logic programming?
There is
Uh,
a section of chapter 9 dedicated to that, 9.3.
Relation to logic programming. Yeah, I'm very excited. Logic and logic. Is this a typo?
No, it's logic as in, the thing that logicians do, and logic programming as in the thing that Prolog people do.
Okay. I'm very curious to know if I can identify the difference because to me they are no different. But we'll see. So chapter 8 is next time, and I guess we're gonna do it in 2026. Bye.